just to kind of get into like cubic inches and roots type blowers and things of that such. At any rate, so you have 671, okay? Now you have a small bore and large bore. So way back 18 some odd 60s, something like that, Philander and Francis Roots came up with a design, a blower that would push air through their furnaces, and these furnaces needed to get really hot really fast, and they later got the name of blast furnaces. So the blower was originally designed to move air through furnaces, and about 2 years after the first invention of the four-stroke engine, I think a guy named by Dougal Clerk, he actually put it on a two-stroke engine and made a compressor design of a actual reciprocating piston compressing air and being plumbed into a adjacent cylinder. And if you look at this engine, it looked like a V engine, but it's not a V engine. It's basically just an offset of another cylinder used as a form of compressing air to feed another cylinder. Dougal Clerk, and I hope that's that guy's name. But anyways, he used a piston type, so he needed a way to move air through his two-stroke engine. And basically, if you look at the modern design of the two-stroke engine, when the piston descends down the cylinder, it actually creates a compression in the block area, where it then goes to a transfer slot, and it actually feeds into the cylinder. So when the piston descends in the modern two-stroke engine, basically the air below the piston compresses that chamber and forces it to the top of the intake. So that's how the modern two-stroke works. And Dougal Clerk actually had like a two-piston. It wasn't really a supercharger per se, but it kind of feeds into what the story is in the supercharger. Moving forward on some supercharging history. Now this is supercharging in general. This could be a means of piston, it could be means of rotors, it could be means of valving, reed type, or just the actual function of the motor itself. So supercharging in general is something that's driven off the it's driven off the engine and is basically controlled by the engine, any RPM or pressure per se. So I think it was Gottlieb Daimler, who made this tall engine, okay? And this engine basically had like a valve and a piston, and the actual valve would open and charge the intake, pushing more air in the intake, virtually kind of supercharging the idea. Now, when that happened, when he put a Roots type supercharger on a four-stroke engine, something happened. He passed away, or at any rate, his son Paul took over, Paul Daimler, and he started experimenting with putting these Roots blowers on Mercedes cars, and I think they're like 20 or 30 horsepower, something like that. So up until this point, talking about superchargers, the rotor design, the rotors were basically straight, okay? They didn't have the tooling or the manufacturing means of actually making a screw type. So later on, for the furnaces, a guy named Krager, I think Krager, and he actually found a way to make a screw type to the rotor design, to the original rotor design. Now the screw type actually took the rotor, and he had two rotors, okay? One of them facing 12 and 6, and the other one facing 3 and 9. And what it did was Krager actually took that design, and if you compare the face of the rotor to the rear of the rotor, or the back of the rotor, it was actually clocked a quarter turn. So it had like a screw type effect to it as you would travel linear down a rotor. So this Krieger guy had a patent on this design, and sometime after the patent wore out, and this guy named Alf, so he basically took that screw design and he messed around with the idea, and he came up with a lightweight version for turbine engines, and he took that and he formed a process, a way of processing these Roots type blowers, and to where they're lightweight and very functional, and you can add them to basically pretty much everything. So they took that screw design and they ran with it. So being that it was lightweight, they improved the design, and they became what is now known as SRM. Basically any kind of turbine roots type supercharger has an SRM kind of patent on it. So why is this important? Well, it gives you a brief history of how the blower slash supercharger was invented. Now, later on, they started using this in aircraft, and the guy by the name of Rudolph got to about 10,000 meters up in the air, and his eyeballs almost froze. So, without going into that, let's talk about the 671. Now, the 671 supercharger, roots type supercharger, is a positive displacement supercharger. And I use that term loosely, positive displacement, because it's not 100% efficient positive displacement pump. So when the 671 was made, it was on a Detroit diesel, and tolerances were loose. The thing was sloppy, to put it lightly, and these clearances were set like that. These tolerances and clearances were set like that for, you can get in this, get in a vehicle, you start it up, and you go cross country, and you not have to worry about it. Now later on, the clearances started getting tighter when people started manufacturing them, taking them apart, making things a little tighter, and then eventually going to a Teflon strip, to where it would be pretty much 100% volumetric efficiency. And those type of blowers are highly expensive, and they don't last long. They need constant rebuilding. So, but if you were to take a 671 off of a Detroit diesel and you stick it on a regular vehicle, that is not 100% efficient. To give it, I would have to say the efficiency is like around 80%. Okay, so why 80%? Well, for one, the loose tolerances. The clearances they're pretty wide range, and with it being out of aluminum, the expansion when it heats up, and actually the function of compressing air and generating more heat, it becomes less efficient, to the point where you get to you can only throw so much boost at an engine to where you don't get the return that you would think you'd get. So, and boost is directly related to resistance, okay? So you're just moving air. Without resistance, there is no pressure, there is no boost effect. So 671 got its name from 6, meaning the 6-cylinder, and 71 meaning the displacement of that cylinder in the Detroit engine. Now, in the Detroit engine, it was just an air mover. It wasn't a blower, it wasn't a supercharger, it was just an air mover, a blower. So when the piston came down, the blown air would sweep across the cylinder, sweep across the head of the piston, and move it out the exhaust. And the fresh air from the blower would enter the cylinder, piston would rise up into the a chamber, and then you get your diesel injection and have your power. And when the piston comes down, again, that air is being moved by that blower, pushing it out the exhaust. So that's a very crude way of putting the Detroit diesel, but they made a small bore and a large bore. So the small bore, if you take the face of the blower off, the end caps, if you will, and you look at the top, you got your two rotors. The top, if you look at it, it has two crowns, okay, and then a flat spot. That is a small bore 671 blower. Now, without getting into exact numbers, let's just use even numbers just for means of being simple here. So you deal with a 671 that is displacing 420 cubic inches. So you got your 6-cylinder times 71, there you get your 420. And then you got a large bore 671, which displaces roughly about 10% more. So you're actually getting about 446, around 440. So you have a small bore displacing 420, you have a large bore displacing 440. Now, you put a 671 large bore blower on a, let's say, 440 Chrysler. And what happens is you don't actually get zero pressure, atmospheric pressure. What happens is it actually, because the blower is made so loosely, it actually bleeds through and you don't really get that correct boost number, because these things were originally made to blow air, not compress it. And when you stick it on an engine of smaller cubic inch, it then becomes a compressor. And again, due to the tolerances and the heat build and the heat generated when you compress such air, you get to the point of diminishing returns. So how efficient are these? Well, they're roughly about 80% efficient. Now, why do I say 80%? Well, because most of the blowers, they have over 100,000 miles. When people rebuild them, they just freshen them up, and usually sanding out the housings and refreshing that way. They're not actually putting them in a mill and tightening up the tolerances and clearances. And so let's go with like 80%. So 80% of the 420 is around roughly about 360. So 360. So now you got a used Detroit 671 blower on top of a 440 engine displacing 360 cubic inches when an engine, the engine wants 440 cubic inches. So what happens there is you create vacuum. Yes, you are actually somewhat forcing air in there, because remember, the engine without the blower actually creates a vacuum higher than where if you were to displace air and push it easier in the intake. Okay, so you're still creating vacuum. Okay, so even though you have a large bore roots type blower on a 440, you will see vacuum in the intake under the blower. Okay, so now you have a blower displacing 360 cubic inches of air on a 440, and because it's displacing air, it's creating heat and it's creating drag on the motor. So you can see how the diminishing returns comes into play. Now, let's take a manufactured one. Okay, so we're looking at a 671 that has been milled to tighter tolerances. Okay, that's still streetable, so you're probably getting around 90% efficient. Okay, still not enough for that 440. So however, you are pulling less vacuum and you are creating yet more heat. So at any rate, when you go to put one of these on your engine, you can't use exact figures. There's always going to be a lack of volumetric efficiency with these. It's not going to be 100% efficient. It's not even going to be 95% efficient, and I doubt it'd be anywhere near 92% efficient. So that's why a lot of people overdrive these units. Now, when you get to overdriving, it's still not enough. So let's take the same 671 and let's put a 20% overdrive on it. Now, having a volumetric efficiency around, I don't know, I gotta, this math is killing me. I'm gonna have to do this math somehow. Let's say it's 85% efficient. So you got a 671 blower displacing 426 cubic inches of air. Let's say it's 85% efficient. So now it's at 362. All right, so you got 362 cubic inches force fitting a 440 Chrysler. Okay, so as you can see, that is still creating a vacuum. And when you run into a situation like that, it's going to actually make the engine run rich, and it will make the headers glow, it will make the plugs turn black, it will foul out plugs, it'll be very fast starting. So let's do some math. So you got 671 and we overdrive it by the small bore. Let's talk about the small bore only. 671 small bore, we have 85% efficiency, which is 362 cubic inches, and you take that, you add a 5% overdrive pulley, and now you're pushing about 380, okay, because it's 5% overdriven. So 380 cubic inches supplying a 440. It's starving the 440. So you Now let's look at the 671 for the large bore. Now the large bore displaces 10% more, so now we're at 382 instead of 362. Now you add a 5% overdrive pulley to that. 5% of course is 19, and then you get around 401. Okay, so 401 cubic inches feeding a 440. It's still starving the 440. The 440 is actually creating a vacuum in the intake, so that is yet starving the engine of air and it forcing it to run rich, because you still have the signal going to carburetors feeding it fuel, and it will turn the pipes red. So this is the problem, and this is why I say you got to add more boost. When you add more boost, it actually forces more oxygen in there. So let's go to 20%. So 20% of 362 is now 72. 72 plus 362 is 434, and that feeding a 440 is more like it. So let's do the large bore now. So you got a 671 large bore displacing roughly 10% more cubic inch, 382. You got 382 plus the 20% is around 76, which will give you 458 cubic inches of air, force feeding a 440. Now, it gets to the point of diminishing returns because the more air you compress, the hotter it gets. So you get diminishing returns when you start upping the percentage of the overdrive. And when you up the percentage of the overdrive, not only are you creating heat, but you're creating more resistance, because there's called a coefficient of an actual cylinder, tube, hose, call it what you will. There is a friction coefficient. Now that friction coefficient can be a port diameter, it could be port shape, it could be the transition areas, it can be if the gasket's overhanging, it can be the valve in the way, the valve guide extending into the port. It can be, let's say, across the cylinder chamber design. It can be the actual dome of the piston, the exhaust valve, the cuts on the exhaust seats, the cuts on the intake seat, the diameter of pipe, the length of the pipe, how the exhaust is made, how many bends in it, everything comes into play. Even cam design, lobe separation angle, duration, lift, the ramp rate, everything comes into play. So as the resistance goes up and the air is actually, the supercharger is actually being forced to work harder, those tolerances, it stacks up to the point where the diminishing returns is it's actually blowing past the rotors and it's not creating enough boost, and it gets to the point where you don't get anything from it. So and you can do E85. Nitrous works to little effect. Actually, nitrous doesn't work that good as you would think. E85 does work, but only to the point where you get like 30, maybe even 40 degree difference. But at any rate, the lack of air going through the engine, it will turn your headers red. It will turn your plugs black, and there is a dynamic algorithm that is it's undoable. So that being said, just note that supercharging is not a 100% positive displacement pump. It is only as efficient as the person who's building it, the clearances, the tolerances, the heat and resistance.